Yeah, so good morning. Today we will discuss about certain important time frequency pairs. So we make use of continuous time Fourier transformation. And let's take our favorite real-time function or real-time signal, that is a cosine wave. This cosine wave is periodic. This guy is going all the way from negative to positive infinite, and say this is your cos omega naught t. Okay, now as we know very well, if we go to its frequency domain, let me apply continuous time Fourier transformation. So you would see a couple of delta functions. So this is your omega scale, and say this is your x of j omega. And yeah, so this one I'll be having a spike. So at positive omega naught, I have a spike with amplitude. When I say spike, you can treat it as an impulse function or delta function otherwise. So at omega is equal to negative omega naught, again you have positive pi. So this is magnitude of the spectrum, okay? Spectrum of cosine omega naught t. Now, for the time being, you forget about the image of this guy. I mean, what I mean to say is you assume that you have only positive frequency spike or component and forget about this negative frequency component. But without this negative frequency component, you cannot again construct the real signal in the time domain. One should understand this. And this is what the negative frequency will talk about. Negative frequency combined with positive frequency will always represent a real signal in the time domain. If I don't take this negative frequency component, now I will end up with a complex signal in the time domain. Anyways, we have a detailed video on this in our upcoming videos. You can check about negative frequencies. And let's try to plunge into this particular discussion, time frequency pairs. Now, there are certain takeaway points from this. Now, what you have to understand is this. For example, as we forget about, for the time being, we forget about this negative frequency component. Now, say you have a single frequency component like this. So what can we infer from this? Yeah, of course you have that means this is a single tone signal. When I say single tone, you have a single frequency component in the spectrum. Okay, so there is a certain takeaway point from this. That point is, if this cosine function or whatever sine function, whatever you take, if this function is oscillating at certain frequencies, say this function is oscillating, I have here omega naught, right? So this is twice pi f naught t. So if this cosine function is oscillating at say 1 megahertz, okay, assume it is okay, or some 10 megahertz we will take, say this is some radio frequency carrier, RF carrier. Now you can find the spike. The spike you can also find at same 10 megahertz. Okay, if I take this as frequency scale, linear frequency f, then I can observe a spike at 10 megahertz, and I don't see any other frequency components, okay, in the spectrum except one. So therefore, we call it as a single tone function. So this is simple and very important takeaway from this. Now let's venture into a second one. That is, for example, let me take impulse function. Okay, so impulse function is physically impossible, right? Because the function existing at with no duration of time, that is physically impossible. Okay, so let me take, say, an impulse function. I have an impulse function like this, on time domain. Okay, now what must be its spectrum? Its spectrum, if you take, you will see, okay, I'm just taking F here, okay, not omega. Now I would see a constant spectrum like this. Yeah. Now see, for example, what is the, I know what is the instance of this? I mean, how I can say this impulse function? How can we characterize this impulse function like physically? For example, say in a room, say someone is clapping. Okay, say someone is clapping. Now that someone is clapping, we can model that, say we can consider that as an impulse function. And if you're interested to see the frequency components of this impulse function, the spectrum is flat. The spectrum is flat like this. Okay, the spectrum is so on, it's flat for, I mean, for all the frequencies. That means we can say, it's like theoretically what we can say is that the spectrum of impulse function contains like every frequency. Yeah, see, it contains every frequency here. All the frequencies are involved in this, in the spectrum of impulse function. Okay, so this is a very strange behavior, right? But in reality, if you see in what happens is it's like zero time. Okay, so the width is the time duration is zero, and it's highly impossible to produce a signal over a time width of 0 seconds. Okay, in reality, what happens is you would see something like this in reality. Okay, like you know, there will be some, this is something like impulse function, and now say this is your delta t. Yeah, this is your delta t, and delta t is very low. You can say approximately 0, but delta t is not exactly equal to 0. You can make this delta t as low as possible. In practice, you can take, say, up to some 10 to the power of -5 seconds or -6 seconds. Okay, so this is practically a good, I mean, a good characterization. You can't really, I mean, it's not good. It's like ideal. This is something like ideal case. Delta t is equal to 0. Okay, and you can take it as a homework. Now, how would be the spectrum for a function of this kind? That means delta t is not exactly equal to 0, but it's close to 0. Will the spectrum remains flat or not? You just try it as homework. If you want, you can write as a homework. Okay, now there is one important takeaway from this time frequency pair. Yeah, and that important takeaway is that if there is a quick change in time domain, and the consequence of that is you will see many frequencies that occur in the spectrum. For example, you see, I have this impulse function like this. It's like a quick change in no time. For example, you're clapping in a room, okay, in no time things have happened like this, and the frequencies, you are seeing all frequencies in the spectrum. Okay, so that's the takeaway, because as there is a quick change in the time domain, you will see many frequencies. So very important points are this: a quick change in the time domain. See, this is the lovely concept of Fourier transformation. If you understand these things in practice, then you will definitely fall in love with Fourier techniques. Otherwise, Fourier techniques will definitely haunt you, like, because if you don't understand things, and if we try to memorize and solve some problems, it doesn't serve any purpose. Okay, so quick change in the time domain, and this will produce like many frequencies. Okay, many frequencies in the spectrum. When I say spectrum, I have range of frequencies. Okay, so certain frequencies will have high energy content, when compared to others. Now with this motivation, can we guess the spectrum for a square wave? For now, let me take a square wave. I'm not exactly drawing on to scale. So let's take a square wave. So yeah, okay. I'm taking a square wave. Say I have some square wave, something like this, so on. And of course, also towards this negative side, you have, yeah, you have something, say, like this, from negative infinite to positive infinite, you have a square wave. Say, this is your square wave x of t. Now, a quick change, if you see a quick change in the time domain, that results like multiple frequency components in the frequency spectrum. So with that motivation, what can we expect in the frequency domain? So this is straightforward. You will have to understand this. I'm not showing the negative side of the spectrum. Let me take for now the positive side of the spectrum. Let me change this color first. Yeah. And okay. So you have, of course, negative side of the spectrum also you have. See, that means whenever you have a real signal in the time domain, you will definitely see negative frequency components in the frequency domain. That is most important point to understand, okay? And of course, the negative frequency components, whatever we are seeing here, so these are just image. This is an image of this positive frequency component, okay? And of course, it aids in mathematics, I mean mathematical treatment, or things become that simple anyways. Let's not go to that technical jargon, I mean that mathematical jargon for now. Let's try to emphasize the physical or the theoretical aspects of the time frequency pair. So when you see, as we have square wave, now I would see something like this in the frequency domain, like I will have some frequency spikes, something like this, so on. In reality, you will see like all sinc functions here. Like, see, this is like, I can take like all sinc functions I can take in reality. Okay. So, but for now, just okay. In reality, you have something like this, all sinc functions. Also, you have towards this negative side. Let's skip for the time being. Now, what you can understand here is this. See, as my time domain signal has quick changes, okay, quick changes, and I mean, in my time domain, I'm seeing many frequency components in the frequency domain. So this will continuously go on like that. It keep on going that way. You can see some sync behavior on the frequency domain, okay? Now, the quick takeaway, of course, is this, the quick take. I'm taking magnitude of the spectrum, okay? Now, if you observe carefully, this is the strongest spike I'm seeing here, okay? Strongest spike means I have frequency component with high amplitude, okay? Now, you know what, at what frequency you get this, the very high amplitude stuff? That is what the frequency of the square wave. This is a very important takeaway. This we have to absorb. For example, this is say this is capital T. Now from capital T, I mean, of course, we have 1 over f is equal to capital T. Now in this case, this f, say f is equal to say some, okay, let me take some 1 kilohertz. Okay. Now this is this 1 kilohertz. Okay, that means say t is equal to what we have here, 1 millisecond. If t is equal to 1 millisecond, f must be 1 kilohertz, right? That means you have a 1 millisecond period square wave in the time domain. Now you will see the maximum spike in the frequency domain at same 1 kilohertz. And of course, you have other frequency components as well. and significantly their amplitudes, gradually fall in the spectrum. So this is very important. I have quick changes in the time domain, therefore I have many frequency components in the frequency domain. So yeah, and this is of course one of the important observations with the Fourier techniques. Okay, so this is 5Z NR. Okay, 5Z new radio. Anyways, we'll discuss this 5Z new radio things in 9 our subsequent lectures. So next one, see, I have impulse in the time domain, and I can see a flat frequency spectrum. Okay, I can see a flat in the frequency. This is time, and this is frequency. What if I take a constant signal? Okay, let me take a DC function. I'm just taking one side. You can consider the negative side also. You can take, let me take one side like this. I have a DC function. Okay, this is my x of t. I have a constant function. That means what I mean to say is this. Okay, so now if I take its continuous time Fourier transformation, so what we get here? Any guesses? Yeah, this is of course a real signal. So yeah, let me take, this is my x of j omega spectrum. Okay, now the important point to note down here is that will DC has any frequency here? An ideal DC function will not have any frequency component in the spectrum. Yeah. So as there is no frequency in this frequency domain, that means I can select this at f equal to 0, I can take a component. This indicates what, there is no frequency component. So what we can see, but we are seeing some red spike at f equal to 0, but you're seeing a red spike, you're seeing it f equal to 0. F equal to 0 means there is no frequency component in the spectrum. So when there is no frequency component, but still you're seeing a spike, this indicates that, so this quantity is your DC quantity. Yeah, so you can say it's an average value, otherwise it's a simple DC. You can call this as 0H in the frequency domain. Yeah, and because this is due to a DC signal in your time domain. Yeah, because of DC signal in your time domain, you are seeing that DC value, yeah, at f equal to 0. So a constant function like this in the time domain will not have any frequency component. Yeah, so there are many more things to go with, and we will discuss things in the subsequent lectures. And our next thing will be, for example, if I take our next topic will be this. If I take 5Z new radio, 5Z NR approach, in that, for example, if you take a symbol duration, I take a symbol duration. So symbol means I'll be having some multiple bits involved in the symbol. Now, if you pump more number of bits in the symbol, that indicates that you have high data rate or you have faster rates. And if you want to achieve faster rates, so fast data rates can be achieved only in high bandwidth regions. Okay, you must require high bandwidths. And how this time scaling and frequency scaling properties, they talk about high and low bandwidths, or fast or slow symbol rates or bit rates, all those things that we'll investigate when we discuss about that scaling properties in both these domains. And therefore, the reason you'll have to understand is that if you want very high bandwidths, otherwise, very high data rates in very high bandwidth regions, that is very, very costly. That is like in crores. Okay, the investment will be in terms of crores, not even lakhs. So that interesting thing we will discuss. So of course in this course. So our prime focus is like exploring 5Z techniques. But before we venture into actual 5Z, scenario, we will have to understand some basics of signal processing. So I cannot devote all the time for signal processing because we need to plunge into 5C techniques. So we are covering some nuances of some basic nuances of signal processing. Okay, anyways, that's it. Thank you for now. So you can check with negative frequency concept in detail in our upcoming videos. Okay, thank you. Yeah.